Left off last time is we were just starting to talk about pharmaceutical treatments for anxiety. And I think we mostly focused on benzodiazepines. And the basic story is that one of the explanations for what is going on with people that have anxiety, and this could be kind of like maybe not the initial cause, but a consequence of the prolonged cortisol that they tend to be experiencing, and some of the other issues that they're having, is that they seem to have decreased numbers of GABA channels, or at least they have decreased numbers of binding sites for benzodiazepine, which is what specifically is being measured here, such that this person who's an anxiety patient has fewer red spots compared to these red spots that are over here in the control individual. That indicates that they have fewer of these inhibitory channels, these GABA-linked channels, than a normal person. So one thing we can do is we can give them benzodiazepine, which serves to bind to this site right here, and it facilitates the opening of those receptors that they do have. So they're not increasing the receptor number per se, but we're making them more responsive by having benzodiazepine present to any GABA that might come around. And so as a result, they'll get a better response, more inhibition, and that inhibition hopefully will lower some of the overexcitation that's occurring that's leading to the anxiety. Okay. Also, I think we mentioned alcohol has a very similar mechanism. It binds to the same receptors. It's not the exact same binding site, but it does a very similar thing. And the issue with that, of course, is that it does result in alcohol being a fairly effective mitigator for anxiety. Unfortunately, alcohol is also highly addictive, and so there's a pretty strong comorbidity between anxiety patients and alcoholism. They tend to get both. Another kind of treatment for anxiety disorders can include serotonin selective reuptake inhibitors, or SSRIs. These guys have a very different kind of a function. And they're dealing with different receptors than we were dealing with the benzodiazepine. So the idea here is that here is a presynaptic cell that's releasing serotonin as its neurotransmitter. And the serotonin would come over here and bind to receptors, and there's a wide variety of receptors. If you're in neuroscience seminar, the last paper was all about this stuff. However, what this drug does is that normally after serotonin is released, it is quickly transported back into the presynaptic cell by a serotonin selective transport molecule, which is what this guy is right here. So this reuptake transporter. So it's binding up serotonin, pumping it back in. So when you take an SSRI, a serotonin selective reuptake inhibitor, what it's doing is that it's inhibiting your ability to reuptake serotonin. And as a result, serotonin lingers in these synapses for extended periods of time. So as a result, you have ongoing chronic stimulation of these serotonin receptors. This seems to be particularly helpful for OCD patients, so obsessive compulsive disorder patients, in treating the anxiety that accompanies that particular disorder. And it probably has to do with the specific mechanism. But the mechanism is less clear, because clearly what is happening is while SSRIs are effective in reducing some of the symptoms of anxiety, it's not just because there's increased serotonin levels across the brain because you have less uptake of serotonin. And the reason we know that is that when the serotonin is released, I kind of fouled that explanation up. Let me start my sentence over. The reason we know that it can't just be elevated serotonin levels is because the elevated serotonin levels happens basically instantly. So you give somebody an SSRI, and instantly they will have elevated serotonin levels present within all the synapses of their brain. However, any kind of effects that are mitigating anxiety do not happen right away. They might take 2 or more weeks to actually start to be detected and cause changes in behavior, changes in anxiety level. So it's clearly not just the fact that serotonin is present, period, that's causing the issue. One possible mechanism that seems to be consistent with this is that by having elevated serotonin levels present within synapses, this seems to cause an upregulation of glucocorticoid receptors in the hippocampus. And that won't happen right away. That happens over a matter of a couple weeks. So what do you think having more glucocorticoid receptors would do for you? If we sort of think back to what we were talking about as far as mechanisms of anxiety, what would having more receptors for these glucocorticoids in the hippocampus, what could that do for us? I'm going to flip back a slide or two as you're thinking. So if we upregulate glucocorticoid receptors on the hippocampus, what's that going to do? Think it out. Yeah, right? So the hippocampus, where does it say this? Hippocampus has glucocorticoid receptors. And one of their apparent main jobs is that they allow cortisol to stimulate the hippocampus via these glucocorticoid receptors. And when that occurs, the hippocampus then, in turn, inhibits HPA axis. So you decrease the amount of cortisol that you're producing as a result of this. So the function of the SSRIs, at least in part, seems to be to increase the number of receptors hippocampus has for cortisol, which will cause increased inhibition of the HPA axis. That's not going to happen instantly because it's not just responding to serotonin. It's sort of a it's kind of like a long-term, effectively it is a long-term potentiation, a long-term adjustment of how many receptors hippocampus has for cortisol. But it's responding apparently to the serotonin levels. Does that make sense? So at least we have a mechanism there. A lot of these things, a lot of these compounds, sometimes there probably are other mechanisms we just don't even know about yet, and we don't completely understand how they work. Sometimes it's just kind of by chance. There are other options, of course, for treating anxiety than just straight up pharmaceuticals. So again, psychotherapy, talk therapy is really important. The argument here, what you're trying to do from a biological perspective, is that by talking through past events, rehearsing, thinking about, recording, documenting, you encourage the patient to start to effectively rewire some of their synapses. I mean, this is basically a learned response where you're trying to relearn certain responses and relearn and rewire your synapses such that you're retraining your brain to have new synapses to deal with frightening events in different ways. And so hopefully by doing this talk therapy, you can help to reorganize your brain and therefore reduce the degree to which you're exciting anxiety or fear responses or stress responses to day-to-day stimuli. There are some other options that are sort of coming in the future. So your book talks about one of the current sort of promising directions that people are pursuing is to get CRH receptor antagonists. CRH receptor antagonists would block corticosteroid releasing hormone. So if we're blocking CRH, then we therefore, and that's going to be occurring on the pituitary gland, we then would block adrenocorticotropic hormone, which would then ultimately block cortisol production. So we're sort of trying to interfere with the HPA axis via these kinds of things. There's some interesting things like additional details I hadn't really heard before. So one of the efforts here is not just to block the receptors for CRH that would be existent on the anterior pituitary and block the HPA axis, but even if you look into the central nucleus, this guy of the amygdala, we said this is the center where the amygdala is receiving sensory information from all over, and then that sensory information that is determined to be fearful gets relayed to the central nucleus, which then responds and then triggers fear responses elsewhere, like in our hippocampus. The neurotransmitter actually used in central sulcus, or among the neurotransmitters used, is CRH. We usually think of this as a hormone, but it seems like it's actually being used as a neurotransmitter here. So these antagonists, CRH antagonists, have the potential to not just block the HPA axis, but maybe also block some of the activity of the central nucleus and cut down on the fear responses before we even get to the HPA axis. So for this reason, this is thought to be a fairly promising avenue. Questions? What can I do for you? Is that okay? So like from this section, you should definitely know the HPA axis really well. You should understand also, I'm skipping back here, so there's HPA axis. You should understand role of amygdala in terms of stimulating hypothalamus, which then ultimately leads to HPA axis activity. as well as some of the other responses that occur in the fear system. So make sure you I mean, again, that HPA axis I think is really important. Okay, so that's pretty much what we've done with, what we're going to do with anxiety disorders. So what's left then is to look at affective disorders, so basically disorders of mood, depression, and mania. And then also after we do that, we'll turn to schizophrenia. So affective disorders, again, these are disorders of mood. And there's two sort of extreme versions of these. And they are, unfortunately, not independent of one another in all cases. So one major and very common, unfortunately, affective disorder is major depression. So major depression is lowered mood and decreased interest or interest in personal activities or other sorts of activities. And everybody goes through some level of depression at some time, but it's not major depression per se. Major depression is a much more extreme version of this. Diagnosis often requires, like typical, among other things, requires you to be experiencing this kind of thing every day for at least 2 weeks in a row, and certainly it can last years and years when you're going through a depressive episode. Another characteristic of major depression is that it's not necessarily or not obviously always related to some particular event that causes bereavement. So if you get really depressed after a family member dies, that doesn't necessarily mean that you have major depression. It means that you're going through a normal sort of grieving process. Although that doesn't mean that that can't lead to major depression, but it's not always obviously related to bereavement per se. It's really important from a healthcare perspective because it is the main precipitating cause of suicide. So the reason people commit suicide most often is due to major depression. And so as a result, this is a fatal disorder in that way. So it's certainly something that's very important to understand and ultimately combat. It's also 2 times as likely to be, it's 2 times as common in women than men. That's not to say men can't get it, but women seem to be much more susceptible to it. There's other varieties. So like that's major depression is sort of like the major depression with an MD. So like, you know, or major depression disorder is the MDD is the other terminology for it. There's other forms of depression. So there's dysthymia or dysthymia rather, which is sort of a less severe but also chronic form of depression, but it's not as severe as major depressive disorder. So that's kind of like the down version of the mood. On the other end of that is bipolar disorder, which among other things, the thing that really characterizes bipolar disorder is that you have these recurrent bouts of mania. And sometimes it's called bipolar disorder because sometimes people seem to alternate between the mania and then depression. And they seem to, you know, bounce between them. So they can't seem to, you know, maintain sort of stable mood. They tend to be either in a manic phase or in a depressed phase. There's different varieties. I should define this is, so what do we mean by mania? So mania refers to sort of an abnormally or persistently elevated, expansive, or irritable mood. So this is where somebody is just really, really, really high, not necessarily happy, but full of energy. I mean, they can be very happy, but also full of energy, highly distractible. One of the real characteristics things about mania is that you tend to have really severely impaired judgment. And so people will engage in all kinds of risky behaviors, be it jumping out of airplanes or throwing away all their money into investments that may be not well considered, sexual recklessness, you know, so promiscuity, that kind of thing that tends to occur during these bouts of mania. People have extremely high self-esteem, probably to a deleterious degree because, again, they make really bad decisions and are overconfident. They also will describe their thoughts as just racing. So I don't mean by racing thoughts as in wanting to get into a race car, although they probably would because they're having decreased impaired judgment. But they, you know, the thoughts are just constantly racing and not necessarily following sort of a straight path. They're just, you know, they're constantly just sort of whirling around in their minds. There's sort of 2 forms of bipolar disorder. There's type 1, which is kind of the classic form, where you do have a classic mania incidence, but it can be either with or without alternations into depression. Whereas type 2 is sort of less severe, where you have sort of a hypomania. So you're still manic, but not to the normal sort of true mania with a capital M. But the thing about type 2 is that while you'll go into these mania phases, it always is accompanied by major depression, basically just by definition. We're going to not get into all those details. Really what I want to emphasize, or what I want to use bipolar disorder for, is as a contrast to depression. So we can try to understand what's going on when somebody's depressed, but also then try to understand what's going on when somebody's experiencing mania. And that's basically where we're going to be going here. Okay, so how do affective disorders work? A lot of the basis for our understanding for how affective disorders operate, so what is the ultimate cause of them, ultimately has to do with pharmaceutical research, where either a pharmaceutical drug has ended up causing depression in a person, or we've observed those drugs that actually can seem to serve as an antidepressant. And by understanding something about how those drugs work, we can better understand how depression actually typically operates when somebody's experiencing major depression. So here are three, and I'm saying early pharmaceutical findings. These are pretty much all from the 1900s, but 1900s weren't that long ago. I was born in the 1900s. I hope you guys were too, right? Yeah, you were still born. Okay, good. So we haven't quite crossed that threshold. It won't be long. So here are three. First of all, one of the first sort of indications that gave us some clue about where depression is coming from is there's this drug reserpine. And this drug was used as a blood pressure drug. And I even found the label, in fact, sometimes still is used as a blood pressure drug. But one of the things they found about it is that in addition to helping to treat blood pressure pathologies, it also, in some patients, caused really severe depression. And one of the mechanisms by which this seemed to happen is that it released catecholamines and serotonin. Reduced the loading of catecholamines, so this is like acetylcholine, and serotonin, which we've already seen is sort of this major stimulatory neurotransmitter. All of these are amongst those diffuse modulatory neurotransmitter systems we were talking about in the last chapter. So acetylcholine, serotonin, generally are excitatory types of neurotransmitters. It reduces their loading into synaptic vesicles. So what that means is, in between each release of synaptic vesicles, we have to load up more vesicles with the neurotransmitter. In this case, this drug seems to reduce the effectiveness of that, and as a result, the vesicles that will be released will have less neurotransmitter per vesicle. And so we'll have less excitation. I think we would sort of predict then that that's going to result in less excitation and stimulation from catecholamines and from serotonin. Here's another one. There are tuberculosis drugs that were used, and as they were using these to treat tuberculosis, they found that it actually caused a mood elevation. And one of the mechanisms by which this occurred is they interfered with a particular enzyme. It's called monoamine oxidase. Monoamine oxidase is an enzyme that destroys catecholamines and serotonin. So in this case, by preventing, so we're interfering with this enzyme. So by preventing the destruction of catecholamines and serotonin, this allowed for elevated mood levels. So this is pretty, those first two are pretty nice, right? So this is indicating something about catecholamines and serotonin. Here, if it's low, if these levels become low due to poor synaptic loading, then we can result in depression. If, on the other hand, we reduce the destruction of them, so that's going to elevate levels of catecholamine and elevate levels of serotonin, that's going to result in mood elevation. So both of those are nice, I think, and consistent with each other. Here's another one that seems to be consistent. So this drug, imipramine, it's an antidepressant, and as people studied it and tried to figure out its mechanism, what they found is that it actually caused a reduce in the uptake of serotonin and norepinephrine, which ended up leaving them in synapses. So it's not a SSRI because it's not specific to serotonin. Instead, it's causing reduced reuptake of both of these kinds of neurotransmitters, norepi and serotonin. So given all that, what do you think might be causing depression? Like, can we, from those sorts of results, we have an antidepressant here that reduces reuptake. We have a mood elevator that reduces destruction. We have reserpine that's reducing serotonin and catecholamines. So like what could be leading to depressive episodes, perhaps, from these results? Yeah, what do you think? Yeah, that would seem consistent, right? So The first one says if you don't have enough serotonin, you get depressed. The next one says if you've got too much serotonin, you have mood elevation. The next one, it's an antidepressant if you reduce the reuptake of serotonin. So serotonin seems to be a consistent thing throughout this. And I don't think we would completely want to rule out norepinephrine or catecholamines either as being involved. All of these are some of these diffuse modulatory neurotransmitter systems that cause widespread excitation across the brain. And so here, if you are reducing the amounts of those, that's going to lead, at least the hypothesis would be, if we reduce the amount of these types of neurotransmitters, that is likely to lead to depression, and vice versa. If you increase the numbers of them, that should result in increased or elevated mood. So that's very much this first hypothesis here that we'll talk about for depression. So it's called the monoamine hypothesis, that argues that reduced monoamines, so you might remember when we were talking different kinds of neurotransmitters, we talked about peptide neurotransmitters and amino acid neurotransmitters like glutamate or glycine. And then the rest of them were pretty much all monoamines. Those included norepinephrine, serotonin, acetylcholine, dopamine fits in this as well. And the argument here is that by having lower numbers of these neurotransmitters, that this causes depression. Now, kind of like we were talking before, when people have tried to work on pharmaceuticals, what they often find is that the effect is not instant. If you sort of reset or use drugs that increase serotonin levels, for example, like with an SSRI, you don't instantly get relief from depression. Instead, what it tends to happen is that over the matter of a couple weeks, you seem to have changes in the brain that results from elevated levels of these monoamines in response to drugs. And as a result, you get some sort of change in the brain that does ultimately lead to relief from the depression. But it's not just purely the levels of those neurotransmitters that causes it directly. These figures are from, really, they're from this chapter, but they're also from chapter 15. And we kind of cited at least a few of these. So like the serotonin system, we showed up back in the sleep chapter. We talked about this being one of our major excitatory diffuse modulatory neurotransmitter systems, where you've got the Rafe nuclei that are sending axons all over the brain and causing serotonin to be released all over the brain. Here's one that we didn't show. Maybe we did. I don't think we did, though, with norepinephrine functioning in the same kind of way. So here it's released from the locus coeruleus and sends signals to all different parts of the brain, and that norepinephrine causes general excitation most of the places it goes to. So that's a nice mechanism, and there is good empirical data that seems to support this, because if you mess around with the levels of monoamines, you can at least eventually help somebody sort of recover from a depressive episode. There is also evidence that this same HPA axis that we were talking about in anxiety patients often seems to be in play with depressed patients. In fact, anxiety and depression tend to have a strong comorbidity. So again, people tend to have both of these things. And one of the mechanism to me is a little bit less clear. But the idea here is that most patients that are depressed tend to have elevated cortisol levels because they have elevated HPA axis activity. And in fact, this is almost more reliable than them having differences or unusual levels of monoamines as you're going around surveying different depressed patients. This seems to be a really common type of a finding. Furthermore, it's possible at least in animal models, that if you inject CRH into the brain within these animals, so CRH is this is the hypothalamic releasing hormone that is released by the hypothalamus that triggers the HPA axis to run. If you inject that hormone and have increased levels of that hormone present within the brains of animals, you can actually cause them to have depression-like symptoms. So it seems to be that, again, while we tend to think of HPA axis as about stress or maybe about anxiety, it seems to have an important role to play with relation to depression. Furthermore, depressed patients often also have reduced glucocorticoid receptors in the hypothalamus, just like we saw in some anxiety patients. We talked about PTSD actually has reduced, well, that was more hippocampal volume. But the idea here is that one of the explanations for what's going on here is that you have, got ahead of myself again. So one of the explanations for for a linkage here is that it could be, or it seems to be the case, that these glucocorticoid receptors that are present in these different structures seem to be sensitive to early events in life. So one of the experiments that have been done is that if you deprive an individual mouse, for example, of good natal care, so you don't allow them to be groomed by or taken care of by their mother, what they will tend to do is have reduced levels of glucocorticoid receptors present within their hippocampus. While similarly, at the same time, if you allow them to have good maternal care, they will have increased levels of the glucocorticoid receptors. And we've already seen what happens when those are present within the hippocampus. You get cortisol feeding back, and then as you stimulate the hippocampus via these glucocorticoid receptors, that reduces HPA axis activity. So if HPA axis activity is leading to the depression episodes, then the sort of early care in mice that they're receiving seems to increase their ability to ward off those kinds of events. I think interestingly enough, they've even figured out that if they, instead of allowing the mother mouse to provide maternal care, parental care to the pups, even if they just sort of groom the pups, so you kind of give them tactile stimulation, you stroke them a few times a day, you can actually mimic the effect and get good glucocorticoid receptor expression within the hippocampus. Again, indicating that there's something really important about the parental care that's occurring that is helping them increase glucocorticoid receptors in these hippocampuses, which again, the idea here is that if you've got good levels of glucocorticoid receptors, you can prevent overproduction of cortisol, because as soon as cortisol gets super high, hippocampus can then in turn shut down the HPA axis. But if that is impaired somehow, you don't have enough receptors, then you're unable to do that. So that at least shows some of the relationships here that may be going on in terms of what could be connections between the monoamines that we were just talking about on the prior slide. Oh, I'm sorry, I'm not spitting things out very well today. The idea here is that this is indicating that HPA has some role to play within depressive episodes. To me, it's unclear from what we're presenting here what all this stuff has to do in terms of HPA axis and cortisol production's effect on depression. What does that have to do with all the stuff on the prior slide, which was all about serotonin levels and general excitatory neurotransmitters? So the monoamine hypothesis, what's the connection between them? And I think the reason that's unclear is that I don't think it is really well understood. It's, my little bit of digging over the past couple of weeks to try to understand this better has not been particularly fruitful. I did find a paper, so this does show up on the homework. I found other papers too, but this one I thought was more accessible than some of the others, that tries to better explain what this linkage is between cortisol and monoamine levels. So we'll kind of revisit this, trying to connect this slide, the HPA axis, to the prior slide, which is this monoamine hypothesis. So we'll come back to that on Monday. All right, so that's what I'm going to give you in terms of mechanism for depression. So we've got reduced levels of monoamines. We have elevated HPA activity. So how can we then in turn treat? Well, probably not surprisingly, some of the treatments for depression, given that the mechanisms kind of overlap with what we saw with anxiety disorders, some of the treatments are very similar, if not exactly the same. A lot of the pharmaceutical treatments for depression involve some of these reuptake inhibitors. So some types of inhibitors directly block the reuptake of norepinephrine and serotonin collectively. These include what are referred to as tricyclic, tricyclic drugs that are used to combat norepinephrine and serotonin. And basically they prevent the reuptake of it, so you have elevated levels of norepi and serotonin present all the time, and that seems to, again, over multiple weeks, lead to a curing of depression. You also have, again, these serotonin-specific reuptake inhibitors. And here's an example of one of these, where the SSRIs strictly work on serotonin levels, but they seem to work as well. So both of those are actually shown in this figure, if the mechanism wasn't exactly clear. So over here, this one is more similar to the prior figure we had that was just focused on serotonin. So here's serotonin being released. 5-HT is the abbreviation for serotonin. So serotonin gets released, but then serotonin selective reuptake inhibitors, like this guy, will block that reuptake transporter and keep serotonin present within synapses. Again, that's the same thing we saw prior. Here is a similar kind of thing, but this is a different synapse. This one actually involves norepinephrine. And norepinephrine also has a reuptake transporter. That's the way it is cleared out of synapses. While SSRIs do not block norepinephrine, the tricyclic ones typically do, where they're going to block reuptake of norepinephrine in addition to actually having function on serotonin. In all these cases, the point is that you're elevating levels of those monoamines that are otherwise reduced. So you're elevating norepinephrine levels by not letting it be taken back up, and you're elevating serotonin levels by preventing it from being reuptaken. There are other kinds of drugs too. So another one, in fact, we just talked about this one a few slides ago. Drugs are actually manufactured now to specifically cause inhibition of monoamine oxidase. Monoamine oxidase, MAO, is used to break down serotonin or norepinephrine in synapses after they've been released. So to some degree, we pull them back in with the reuptake transporters, but we can also just straight up blow them up, destroy them, just like we did acetylcholinesterase. But in this case, monoamine oxidase will break down either serotonin or norepinephrine, whichever one's present. So these drugs will tend to inhibit that process and therefore prevent destruction of serotonin and norepinephrine, so it lingers in synapses longer. So in both of these cases, or all of these cases, we are increasing monoamine concentration within synapses, and by doing that, we're not immediately curing the depression, but we are helping to increase general excitation, which seems to ultimately lead to changes within the brain that lead to decreased or dampened activity of the HPA axis and lessened symptoms of depression. One cool thing, for example, that seems to happen among other things, so you see increased glucocorticoid receptors present within the hippocampus. SSRIs specifically have also been shown to promote neurogenesis in the hippocampus, so there you're actually creating new neurons present within the hippocampus, which again has this function of shutting down overexpression of the HPA axis. So there's at least there's some signal in there that I think helps to understand exactly mechanistically what they're doing. Any questions on any of that? What about mania? So mania is kind of the opposite situation, where instead of having sort of chronically lowered mood, you have chronically elevated mood, at least while you're going through a manic bout. The main treatment for mania, and so this is the main treatment for bipolar disorder in this case, is lithium, which is kind of a weird drug. So lithium is just straight up an ion. I mean, lithium is we haven't really talked about lithium because it's rarely found in biological systems, but it is, really similar. If you look on the periodic table, I clipped off all the right side of the periodic table here, but there's potassium, so that's a +1 ion, right? We've seen lots of potassium. There's sodium. It also forms an ion that tends to have a +1 charge. Lithium also does this. It's the smallest of these three. So it's here. It tends to have 3 protons. It'll lose one of those, one of its electrons, so it'll tend to be positively charged as an ion. And this stuff seems to have pretty effective ability to combat some forms of the mania. I think the story behind this, your book goes into this, I think it's kind of interesting. The story behind lithium is kind of like, it's almost like penicillin in that it's just sort of like this happenstance discovery that occurred. There's this guy, John Cade, who was an Australian, and he was researching, trying to understand what is going on in the case of people that have mania or experiencing mania, and his hypothesis was that there would be products that would be present within urine that, like urine from these patients, that would lead to or be indicative of the cause of the mania itself. So one of the things he was interested in doing, he had this idea that there was elevated uric acid in bipolar patients, and this elevated uric acid, and he's pulling the uric acid out of the urine, but that elevated uric acid might be causing the increase in mania. So he had this prediction then, that if I get uric acid and I deliver that into, in this case he was working on guinea pigs, but if I give them uric acid, that should elevate their levels of mania. So they should show increased activity and less fear behaviors and that kind of thing as a result of the mania. So he injected them. He had a hard time getting uric acid into solution. Uric acid is just notoriously insoluble in water. So instead he used this lithium urate, which is very similar. Urate is basically uric acid, but it's a lithium salt. And he used that as what he injected into these animals. And rather than showing mania, they actually showed a calming effect, which is the opposite of what he expected. And again, he was focusing on the urate part of it, but he used lithium urate salt in order to induce this effect, and the lithium urate salt seemed to cause them to calm, which I think is kind of fun. So all of a sudden, he kind of discovered this treatment. It wasn't the urate, it's the lithium, but by providing lithium, it seemed to calm these guinea pigs, and it turned out it also seems to work pretty well on people. So great, we have a drug that can be used to help treat mania. The problem is that the mechanism is not super clear as far as what happens. In fact, there's probably a wide variety of mechanisms because lithium, being a tiny little positively charged ion, can get through and go into many different places and interact with lots of different systems. So being a small positively charged ion, it has no trouble passing through sodium-specific channels or any kind of a cation channel. But even like, the voltage-gated sodium channels, for example, that we always said are so specific for sodium, lithium goes right through those. And then once it gets in, it seems to interfere with a variety of second messenger systems. So for example, we didn't talk about this one, but when we talked about neurotransmitters and G protein systems involving neurotransmitters, the main example we used was a receptor like norepinephrine neurotransmitter binds to a receptor. So like if a norepinephrine binds to its receptor, it activates a G protein, which activates adenylate cyclase, which produces cyclic AMP, and so on and so on and so on. I think I said at the time there are other kinds of second messenger systems, and this is actually one of them. So here is, in this case, this is serotonin binding to a receptor. And what it does is it activates a G protein, which activates an enzyme, which creates a second messenger. But in this case, the enzyme is called phospholipase C. It creates a second messenger where basically what it does is it breaks PIP2, which is a phospholipid, into two parts. One of them becomes DAG, diacylglycerol, which you don't have to know. And then you just need to know DAG. The other one becomes IP3. These then have second messenger effects, just like cyclic AMP does. So they can go stimulate channels, they can activate protein kinases. IP3 in this case actually turns into IP2, which activates something called IPP, which ultimately creates this IMPase. I don't think I'm that concerned about you knowing this whole cycle of activity, but the key thing is empirical work has demonstrated that lithium actually comes in and interferes with the activity of this IMPase as well as the activity of this IPP stuff. And so it's reducing the efficacy of the phospholipase C second messenger system that normally would respond to serotonin. So by knocking that system out, we reduce the effectiveness on this neurotransmitter system. In addition to that, there's some data, although your book doesn't provide any figures for it, and I haven't really been able to find many details, but there's apparently also some indication that it can also interfere with that adenylate cyclase cyclic AMP second messenger system. So if the issue here with a manic patient is that they have overactive monoamines or overactive neurotransmitting systems that are going on, lithium seems to interfere with them somehow. And as a result, it'll help to reduce the mania. Does that make sense? Questions? I'm trying to remember, did we, I don't think we really did talk about phospholipase C, did we? I should have checked before now, but I'm just, at this moment, I was thinking initially that we did, but I think I cut that out of our slides. Maybe that has to go back in next year. All right. So we've talked anxiety. We've talked now depression and mania, at least to some degree, more depression, but we did a bit on mania just now. So the last topic then is schizophrenia. And schizophrenia I think is interesting because I think like I said the last time, while everybody at some times feels kind of anxious, And so we maybe can imagine what it would be like to have that system on overload. And everybody's felt sad, and so everybody can imagine what that would be like to have your sadness sort of on override, or running out of control. We haven't really experienced what somebody experiences with schizophrenia most of the time. So schizophrenia, here's basically definitions of your from your book that describes this thing. But schizophrenia is described as a loss of contact with reality, substantial disruption of thought and perception and mood and movement. So, and you can go through and characterize schizophrenia as having a number of symptoms that are either described as positive or negative. Positive does not mean good in this case. Positive means symptoms that are there that otherwise shouldn't be. So sort of unusual symptomology, presence of things that are there. And then negative symptoms refers to absence of the usual in this case. So I'll just sort of run through these. So patients that have schizophrenia often suffer from delusions and hallucinations. So these are things that shouldn't be there and are there. So we consider them to be positive symptoms. But an idea might be that they may have delusions about some. Sometimes people even say, "What is that?" Some people, maybe I'm hearing things. Some people will say that describe schizophrenia as paranoid schizophrenia. And because oftentimes people will have this sort of delusion that people are out to get them, for example, or just as a sort of common thing that you may have heard about. So that might be a delusion. They have this sort of paranoid feeling that there are people out to get them, trying to kill them, trying to hurt them. And then in addition to having those delusions, they may then have hallucinations that are consistent with that. So they may hear voices in their minds saying, "I'm going to kill you, I'm going to hurt you." They may see visual sorts of hallucinations that, maybe they see somebody running at them with a dagger or something, I don't know. And so as a result, these two kind of feed off of one another. So these are things that shouldn't be there. These are sort of unusual sorts of symptomologies. They will often have really disorganized speech, so they may have a hard time being very intelligible as they're trying to explain what they're experienced. They may have really disorganized behavior where they can't seem to have like good goal-oriented things. Well, that's sort of getting into this one, but they have sort of this tendency to have behavior that's highly erratic and not consistent and not directed towards a particular outcome. And then they'll have negative symptoms. So this is where they have sort of the absence of the usual. So they may have reduced emotional expression. They may not express their emotions normally. They may, in addition to when they speak being fairly disorganized, they may have a rather paucity or a poverty of speech where they just don't speak much at all. So that's a negative symptom. They may have difficulty initiating goal-oriented behavior. So they may not be able to start doing some particular thing that's oriented around a particular goal, while at the same time doing all kinds of other tasks that seem to be not oriented towards a goal. And they may have reduced ability to form memories. So it's a really debilitating disorder, to say the least. And I think it's a really interesting one because it does sort of speak to things just not working in the brain and getting away from, it's not just sort of an extreme version of some normal sorts of experiences. There's just substantial changes to what's going on with the person. So what causes schizophrenia? There seems to be a very strong genetic basis. So we'll kind of do, kind of like a paper would do. We'll do genetic, or the sort of basic etiology, and then we'll get into pathophysiology of it. There seems to be a very strong genetic basis. So here is a figure that's basically showing for the number of, as you sort of go from comparisons between random people in the general population versus comparisons between identical twins. So as we move down the y-axis here on this graph, we're going from very few genes shared, at least not any more than would be expected between any two random people, to increasingly strong amounts of genetic similarities. So for example, down here, you get to identical twins, which share 100% of their genes. They're all descended from one oocyte that split right after fertilization into two individual embryos. What you end up seeing is that, again, as that gene similarity increases, the chance that you will have schizophrenia if that other person has schizophrenia tends to increase. So in general, there's about a 1% incidence of schizophrenia. But if you look at, for example, a situation where if your parent has schizophrenia, what's the likelihood that you'll develop it? It's going to be somewhere around about 6%. So you've got about a 6-fold increase in your risk as you're looking at first-degree relatives. Siblings, it's even a little bit higher, which is kind of interesting because they should have the same genetic similarity to you, but there are some arguments about epigenetic effects. If you look at identical twins again, so these are twins that share everything in terms of their genetic similarity at least, there's about a 50% chance that one twin will have schizophrenia if the other one does have it. So clearly genetics seems to be really important in terms of determining your risk for schizophrenia. But, I'll point out also, it's still only 50%. Like there's 100% shared genes here in the identical twin case, but it's only about 50%. So we're kind of out of time. So what we want to try to understand is what is accounting for this being 50% as opposed to 100%. So what are some of the factors that would lead to somebody developing schizophrenia that go beyond just the genetic similarities? And what are the mechanisms by which it occurs within their brains? So that's what we will do next week. Again, I would like to do, as I said at the start of class, go back, go back, go back. We're going to do homework and quizzes also on Monday. So we'll start with a quiz. We'll finish off these slides, talk schizophrenia, and then we'll start into your homework. So have a great weekend.